The second basic problem of hidden Markov model is it's actually more used in real-world applications. This is supposedly we have the parameters for the hidden Markov model. We are also given a string of observations. And then the question is how to predict the hidden states, the paths in order to get there. So what is the hidden coin behind each coin flip? It's like this. Okay, so supposedly we have the parameters for the hidden Markov model. And we observed head, tail, tail, head, 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 tail. So the question is, can we guess at this point what is the hidden states that's used, or at every coin flip that we observed, what is the hidden state? Which is, for example, in the stock market, you can imagine you have observed the stock price over a year's time, sometimes going up, sometimes going down. The question is, can you guess, is January a bull market, February, like you guess at each day, are we in the middle of a bull market or bear market, right? It's going up or down overall. And so we are asked to guess the hidden states, right? And so interestingly, solution for the problem 1 can now be used to solve this problem 2 using a procedure called forward-backward. So remember, in forward procedure previously, we have estimated all the alpha numbers, right? So what is the alpha numbers? Alpha numbers are the probability of using this coin in order to see all the flips up to now, including the current flip and everything before, right? What's the probability of using a fair coin? So for example, in this case, what is the probability of using a fair coin in order to see ahead and everything before? What is the probability of using a biased coin to see ahead and everything before, right? That's your alpha number. That's from the forward procedure. But we also calculate using the backward procedure, going backward. We also calculate these beta numbers. What are the beta numbers? The beta number is the probability of using this coin in order to see all the flips after it, not including this one. That's what the beta numbers mean, right? So it's the probability of a fair in order to see everything after, the probability of using a biased coin to see everything after, not including this particular coin. And so now, can we try to guess what is the hidden states, say at this location or at that location? The forward-backward procedure works like this. So instead of calculating a alpha and beta, we now at each location calculate a gamma number. So the gamma number is like this. We ask what is the probability at this location, in the third position, that we are using a fair coin. You can see that's this is the, we're trying to use these numbers to estimate the gamma 3 of being a fair coin. Okay, so this number is basically, we know that we are trying to estimate the third coin being a fair coin, and we say, okay, we have to look at everything before and everything after. And then we kind of multiply them together in order to see the whole string of, based on the whole string of coin flip, I'm trying to guess at this location, what's the probability I'm going to use a fair coin. And so we multiply the alpha 3 fair coin with the beta 3 fair coin, because the alpha 3 fair coin is in order to see a tail and everything before. The beta fair coin here is the chance of using a fair coin to see everything after, right? So now we multiply them together is kind of the probability of seeing the whole string, divided by what's the alternative, right? So the alternative is at this location, instead of using a fair coin, I'm using a biased coin here. And so if I'm using a biased coin, then the alpha here is, okay, in order to see what is the probability of using a biased coin to see a tail and everything before, multiplied by the probability of using a biased coin to see everything after, right? So now that's the alternative. You can see here. This is the fair coin possibility divided by either a fair coin or a biased coin. And these two have to, these two basically have to add up to the total possibilities, right? And so basically you just multiply the alpha and beta for fair coin divided by the fair coin possibility and the biased coin probability. So this is the sum of the probability, and you get a number. And so if this number is over 50%, you are going to guess that at this point it's more likely to be using the fair coin. And the probability of using a biased coin, the gamma biased, should be 1 minus this number. And you can see that's like a 0.34, something like that. So 0.44. It's below 50%. Which means if I have to make a guess, I'm going to guess at third location, I'm more likely to be using a fair coin than a biased coin. In fact, at each location, we have a probability estimate. So in some locations, I'm super confident. Say, supposedly the gamma fair coin could be 0.99. But some other locations, even though I made a guess that this is a fair coin, maybe the gamma value for fair coin is only 0.55, then you know that you're not so confident. And so the forward-backward procedure, it can maximize the expected number of correctly predicted states. If we are given a whole string of coin flips, say 200 coin flips using coins that are hidden from the observer, and if the hidden Markov model parameters are already given and the observers see a whole string like 200 coin flips, using this forward-backward procedure, if the observer needs to guess at every coin flip which is the hidden states that this guy used, the forward-backward procedure will ensure that if you do this method many times, you try this many cases, overall you will maximize the total number of correctly predicted states, and so you are more likely to give a correct guess, say 150 times out of 200, right? So or to maximize the number of correct guesses. In addition, at every location, at every coin flip, we have a probability estimate of whether this is a fair or biased coin, so you know how confident that guess is. Remember, in the previous problem 1, we had 2 solutions. One was the forward procedure, and the other was the backward procedure. And they both solved the problem, and they gave identical result. For problem 2, in order to guess the hidden states, there are also 2 ways to solve the problem. The first is the forward-backward procedure, and the second is called the Viterbi algorithm. This one also uses the dynamic programming approach, but it's not trying to sum over many conditions. If you think about forward-backward, remember, whenever we're calculating the yellow dots, we're trying to sum over all the previous states or all the states after, doing a lot of summations. Viterbi doesn't do that. So in order to explain that, before we introduced 2 other parameters. One is the delta parameter, which kind of keep track of. It's a yellow dot that we try to keep track of things. And then there's a psi parameter, which is a pointer to remember how we got here. So let's look at the Viterbi algorithm procedure in here. So supposedly we have a string of coin tosses, right? And we keep the original initial probability. So let's see here. Initialization. We know that the first coin, so we calculate the delta 1, which is what is the probability of observing a head coming from a fair coin. So that is, this part is easy. So first we have to use a fair coin. This is the initial probability of 0.4 times the emission probability of using the fair coin to give a head. The delta 1 from the biased coins is if we have to use a biased coin here, multiplied by the emission probability of using the biased coins to give the head, and that's 0.48, right? So that's the initialization. So now we move forward on the Viterbi algorithm. Yeah, so this is the delta 1, and we keep track of these as the yellow dot, which is what is the probability of using this fair coin to see the first head, or using the bias coin to see the first head, right? But then the recursion is different. Instead of trying to sum over all the different paths, the Viterbi algorithm is actually pretty greedy. It just tries to remember the best way to get here. And it doesn't try to sum, instead it's trying to find the maximum. And so I will show you how this is done. So in order to see, okay, if I have to get a tail on the second coin, and we try to get the delta delta fair coin, so which means I'm gonna use a fair coin here. There are two possibilities. One is the previous coin is a fair coin, and I inherit this yellow number, but then transition from fair to fair. Or if the previous coin is biased, I will inherit this yellow dot, but then transition from biased to fair. And so now, instead of trying to sum those two paths together, I do a comparison. This yellow dot multiplied by this transition, compare with this yellow dot multiplied by this transition. I ask, which one is more likely? I only need to keep track of the best paths. And so in here, supposedly this one give you a better number. I think it does if you add up the numbers. So this one give me a better path. So the psi is a pointer to remember, okay, this is the path I took. I did not take this path. And so now we know that from here, if I'm going to use a fair coin, that previous coin I use is a bias coin. And so then I just use this yellow dot, use this transition from bias to fair in order to get to the fair coin now. Sorry. And then from this fair coin, I need to use the emission probability to give out a head. Use this fair coin to flip a tail. So that's the emission probability. And so this number multiplied by emission will give me this new yellow dot. And that's the delta for fair coin. In order to calculate on the bottom side, it's this yellow dot, this yellow dot transitioning from fair coin to a bias coin compared to this yellow dot from bias coin, this yellow dot, and the transition from bias to bias. So this number times this, so the delta number times this transition compared with this delta number multiplied by this transition, and I compare these two, and I only keep track of the best one. And in this case, the pointer, the psi pointer, will remember I'm gonna use the bottom one, not the top one. And so now that I'm using a biased coin, from here I need to emit a tail, and so this number multiplied by the emission probability from a bias to a tail, that's my new yellow dot for the bias coin. So the delta bias at second location. Right, so you can calculate the numbers, you can see. And then we keep going, okay? So looking at the third, we're asking what is the chance that we're gonna use, or what is the path that will most likely that give us the best chance to use a fair coin now in order to give a tail. You say, okay, well, if I'm using a fair now, what are the possibilities? Either previous one I'm using a fair and transition from fair to fair, or previous one I'm using a bias and I'm transitioning from a bias to a fair. Which one is better? I pick the best one. In this case, it's from this yellow dot multiplied by this transition, and now I'm using a fair coin. I emit from this fair coin a tail, and that's my new delta number for fair coin at location 3. We can also calculate the bottom side, which is what is the chance that I'm going to use a biased coin in order to see this tail, or what's the best path to get here using a biased coin here. You say, okay, either I use a fair coin before, I inherit this yellow dot, multiplied by the transition from fair to biased, or I use this, inherit this yellow dot, use a biased coin, and then transition from biased to biased. And so you compare these two paths, and you ask which one has a higher number, and I'm gonna pick the one that's better. And so I know, okay, I'm gonna come from the fair coin to get here, and now that I'm in a bias coin, I need to use this to emit a tail. So that's an emission probability from bias to tail, and that gives me the new delta of bias coin to give the third tail, the third coin flip, which is a tail in here. And we keep going, right? So the delta for this coin flip, if I say what's the probability or what's the best path to get here, if I have to use a fair coin to give this head, it's either the previous is a head, I inherit this yellow number multiplied by this transition, compare with if I previously have come from the bias coin multiplied by this transition, and I compare these two numbers, whichever is bigger, I'm going to use it, yellow dot transition to my fair coin now, and from the fair coin, I multiply by the emission probability to give a head, and that's this yellow dot. On the bottom, it's if the previous coin is fair, I inherit this, do the transition from fair to bias, compare with if the previous one is a biased, I inherit this number, when multiplied by the transition from bias to bias, I compare the two paths, pick the best path, and then that will give me a bias coin, and from here I still need to emit the head, and that's my new number. Okay, and then I just keep going forward and forward. And how does it end at the end? We do something like this. At the very end, we look at the two yellow dot numbers. I was like, okay, in order to get to this head, I could either use a fair coin or I can use a bias coin. Which of these two numbers are bigger? And oh, you say, this one is bigger. This number is bigger. So I say, okay, then this last coin, I should use a bias coin. But in order to use this bias coin, what was the coin that I had to use to get here? We say, oh, we traverse the arrows, the psi pointers to remember how we got here. We say, okay, in order to got here, the previous coin was another bias coin, right? That's how we got here. And then from here, in order to get, in order to get here, we trace again the solid arrows. Say, oh, then the previous coin would be a fair coin. And then from there, using the pointers, we say, okay, the previous one is a biased coin. Therefore, given the current coin flip, the most likely, out of all the possible paths, that single path which will give me the highest probability to give me HTTH coin flip is BFBB. So you can see here, the two algorithms, forward, backward versus the Viterbi algorithm, even though they try to solve the same problem, the final solution may or may not be identical, because their goals are actually slightly different. Okay, because the Viterbi algorithm is asking, there are many possible paths to give me the whatever the string of observed coin flips. Which one is the path that will give me the highest probability of this particular string of coin tosses? That's the goal. Whereas the forward-backward algorithm is trying to guess at each location what is the probability of each node, and its goal is, if I have to make all the guesses of all this node at all the locations, all the times, I want to maximize my total number of correct guesses. And so if you try a Viterbi algorithm versus forward algorithm, most of the hidden states you guess are going to be quite similar, but they are not guaranteed to be exactly identical, because they try to optimize a slightly different thing. So that's the second problem for a hidden Markov model, which is, if we are given the parameters of a hidden Markov model, and also we have a string of observations, how to choose the sequence, how to choose the paths or the hidden states in order to see this observed sequence of coin flips. And there are two solutions, backward-forward and the Viterbi algorithm. They both use dynamic programming, and they should give you fairly similar result, but not necessarily identical.